opportunity to talk about my research. So as the title of my talk suggests, I'll be talking about an intuitive scaffold hopping and bioisosteric modification of known inhibitors towards designing and then synthesizing novel compounds against alpha glucosidase. So before going into the project, let me give you a little background of what alpha glucosidase does. So alpha glucosidase is one of the targets for type 2 diabetes. So what usually happens is, whenever we go for a big meal, like during lunch or for example after the dinner, then alpha glucosidase, it works in our intestine in order to break down the complex carbohydrates into small monosaccharides, and then these monosaccharides cross the intestinal barrier, reaches the blood, and then they are taken towards the individual cells. Then the insulin from the pancreas goes ahead and helps the cell in order to convert those monosaccharides into energy. Now in certain conditions, it so happens that the cells they tend not to recognize the insulin, or for that matter the pancreas secretes less insulin, as a result of which what happens is the monosaccharides which are already in the blood stays in the blood for a longer time, and as a result of which gives rise to postprandial hyperglycemia or blood sugar. Now what typically alpha glucosidase inhibitors will do is they're going to inhibit the alpha glucosidase from breaking down the complex carbohydrates to monosaccharides, as a result of which they will expand the time frame of this digestion, as a result of which at any point of time the concentration of this monosaccharides in the blood will be less, as a result of which the blood sugar level will stay normal. Now there are quite a few alpha glucosidase inhibitors in the market, like as you can see over here, acarbose, voclibose and miglitol. But however, these inhibitors has been discovered about 25 to 30 years back, and until that time no other drugs has come out into the market. And as usual, these compounds are marked with efficacy problem, unwanted side effects. But during this time, there has been a whole lot of research which is going on in the academic field in order to come up with a novel alpha glucosidase inhibitors. So when we started to work on this particular problem, we were thinking about identifying a target-based ligand for alpha glucosidase, and we started looking into these variety, and this is just representative examples, and there has been quite a more different kinds of inhibitors. As you can see, it starts from aza sugars, and then to the chalcones, and then diaryl compounds, galoil, and then these pyridines. So we started to think about how to go ahead and then utilize scaffold hopping in order to develop a new scaffold for our purpose. And then we had a informatics group which we were working with. However, the results which the informatics groups were providing us we were a little bit not very happy. One of the reasons was the kind of molecules they were providing us was not too much amicable towards synthesis. So then we started to look into the molecules manually, went through them, and then we thought about why not go ahead and look into ourselves and try to identify some of these molecules and see if we can intuitively pick them up, join them, and make our own molecules out of that. So it's a sort of an intuitive, we are doing the scaffold hopping, but it's kind of intuitive. And then we thought about utilizing bioisosteric modification in order to make that molecule compatible towards synthesis. Consequently, what we chose was, we looked into these, and then we found that the corresponding pharmacophores of this molecule, if you can borrow them, and then if we can go ahead and merge, hop them, we can come up with this particular compounds. We checked into the literature, and this particular compounds was at that point of time was kind of novel, and like alkyl variation. This was basically, this particular scaffold is from a natural product called serepgene, which contains a methyl group over here, 2 methyl groups. So we thought about probably we can do a condensation reaction over here and we can come up with a library of these molecules. But before going further down, we wanted to see that we wanted to kind of rationalize our approach to see that whether we can really, this is worth moving forward. So we went ahead, sorry for the loss of resolution over here. So we went ahead, we took our desired, designed molecule and the parent molecules, and then we docked them against alpha glucosidase homology model. At that point of time, the alpha glucosidase was not, there was no crystal structure in the protein database. So we developed a homology model based on maltase. Very recently, like about 2 months back, a bacterial alpha glucosidase has come up in the protein data bank. And then we looked into the interactions. We found there are a fair bit of interactions into our resulting molecules when we compare them, the original, their parental molecules, which we can utilize. So we went ahead and we're kind of confident that probably we can get some good interactions out of our design molecules. So we chose, we went through a screening of different conditions, because as a synthetic group, we always kind of remember that when we are trying to synthesize compounds, we would like to do in a combinatorial fashion where the synthesis as well as the isolation and the purification can be done in a parallel manner. Consequently, we chose this catalytic piperidine in ethanol 80 degrees. The good part is we can do it in one pot, these all reactions, one pot in the sense we could do it in a parallel reactor, and when it comes to isolation of the molecules, after the end of the reaction, the products precipitate. We just have to filter and wash them with ethanol, and that's it. So we did it, close to like 22 analogs, we synthesized them in one go. The whole thing took us somewhere around 4 to 5 hours from start to finish, starting from setting up the reaction and then isolating the pure and dry compounds. So as you can see, the yields over here a bit downside in some of the cases. That is because what we found in the reaction mixture, other than when it starts to precipitate, are only these 2 starting materials. The good thing was the precipitate was our product and everything remained in the solution. So we just filtered off, washed them, and then we got our library. So next what we did was we went ahead and did in vitro screening against alpha glucosidase of East origin. And as you can see over here, this particular compound, this 12P with alpha bromothiophenyl aldene pyperidone, was about close to 240 nanomolars. We looked into the SAR, though obviously it's a focus library, but then we just wanted to see how this SAR was developing. So as you can see over here, we started off with aryl groups. Obviously this is necessary. Then we moved into the heterocycles and finally landed up in SAR with the bromo compound over here. We know that bromo compounds have some metabolic issues and they are metabolically unstable, and obviously there are bromo drugs. There's anti-cancer drug, there's antiseptic compound which is bromide itself. So but at that same point of time, this is too early to really predict that how this is going to behave. So we are definitely taking forward this molecule and developing them, but then I will just tell you the initial part of the story. So the next what we did was we went ahead and did a reaction kinetic study. Very surprisingly, this particular molecule gave a mixed inhibition. Now we all know there is a competitive inhibition and there is a non-competitive inhibition. So but then this particular, when we see that it's in between mixed and non-competitive, in between competitive and non-competitive, in the mixed inhibition there is a chance that along with the attack in the binding site, there is also an allostatic attack. There may be. Now what we are trying to do over here is we are trying to go ahead and co-crystallize this molecule 12P along with the crystal alpha glucosidase. Then only we will be able to tell you, but that data is not here as the things are going on right now. So next thing what we did was we just did a normal extracrystal analysis to go ahead and ascertain the structure of this molecule. And then we did a molecular docking in order to understand what are the interactions this 12P has with the alpha glucosidase. So this is the corresponding our molecule with the alpha glucosidase, and this is acarbose, which is the standard drug. As you can see over here, 12P forms 2 hydrogen bonding with aspartame and serine residues and non-bonded interactions with these residues over here. And we also did a molecular dynamic simulation on the homology modeled alpha glucosidase, and as you can see from the MD simulation, we have these H bonding interactions and then hydrophobic interactions with these residues and water bridges. Now we are also utilizing the molecular dynamic simulation to go ahead to understand the binding pattern, but I won't be able to talk to you at this point of time because that result is going on. So another thing what we did over here was we went ahead and did the toxicity studies by taking this molecule and testing them against healthy mammalian COS7 cell line, and it looked like at this IC50 this was non-toxic, and we had to go at least 1,000 times the concentration to show any toxicity of our molecule. So as you can see in the at the end, I can tell you that we have been successfully able to design a small library which works against inhibiting alpha glucosidase inhibitors. We used simple novel condensation, easy synthesis, easy isolation, and then our molecule was about 100-fold more active than acarbose. It's a mixed inhibitor, and we did molecular dynamic simulation and molecular modeling to understand the binding pockets. All of this work has been published in RDC Advanced at the end of last year. So at the end, I would like to thank my group. This is just to tell a little bit about my group. So we dwell into asymmetric synthesis, target-based, DOS synthesis, and then organometallic and organic synthetic metallurgies. These two guys, they are the most senior-most member. Like I started off in 2013. Earlier I was in the industry, and then I switched. And this guy works typically on developing novel oxidative methods towards different nitrogen heterocycles. And this guy works on the alpha glucosidase inhibitors. And this is typically, he's an inorganic chemist who works on organometallic synthesis, and this lady joined my group, and this is an exceptionally talented undergraduate student who is working in diversity-oriented synthesis. So these are my publications in 2015, and these are my collaborators and my funding from Department of Biotechnology, India, and Shiv Nadar University. And thanks a lot to all of you for listening to me. I'm open to any questions. So this is my university. This is the library building, and then this is the new university block where we are stationed.
Thank you, Dr. Sen, for your time.